Hi everybody, welcome back. In our last video we discussed centripetal acceleration and centripetal force involving uniform circular motion, where we got into the formula for centripetal acceleration, A equals v squared over r, and relating it to tangential velocity, v equals 2 pi r over t, allowing us to come up with some other formulas as well by plugging in either for v or for r in our main formula, A equals v squared over r. And then we noted at the end that when you're dealing with uniform circular motion, this is always talking about a force that is causing the uniform circular motion, the centripetal force. In other words, whenever you have uniform circular motion or any sort of circular motion, there must be some agent causing the circular motion, because remember Newton's first law says that the natural state of being for things is to maintain constant velocity, unless acted upon by a net force. So, what are some of these agents? So they can be lots of different things, but the point is to keep in mind that centripetal force is not an example of an agent. Some sort of agent causes centripetal forces, whether it be something like the tension in a string or the force of gravity or something like that. But it must always be caused by some sort of physical agent. So, in other words, something that you would label in a free body diagram. Things like tension or normal force or gravity or something like that. So let's take a look at some examples of these. Let's say you have a clothes washer. What is the agent that would create the centripetal force on the clothes that keep them going in a circle? Well, that would be the normal force in this case. Why do we have the holes? Well, objects maintain constant velocity. The holes are to allow the water to flow out during the spin cycle and thus separate the water from the clothes. Or more precisely, allow the wall to separate the clothes from the water, because the water wants to go constant velocity, but the clothes are being held in by the wall, so the holes allow the water to get separated out. What about a rock that's stuck in a tire tread? Well, in that case, the source of the centripetal force, the agent causing it, would be static friction between the treads of the tire and the rock. Now, I don't have the car in motion clip available right now, but imagine a car going in a circle on a flat road. What would be the agent causing the centripetal force, allowing the car to go in a circle? That would be static friction, assuming that the car isn't sliding off of the road, which it had better not be doing. How about the agent causing the centripetal force for the bank on a curve? Well, in this case, it would be the normal force. Now, here's the thing. The normal force always goes directly outward from the circle. So in this case, on this side, it would go up and to the left. So not all of the normal force would be causing the centripetal force. Only the horizontal part of the normal force would be causing the centripetal force. The vertical part of the normal force would be opposing gravity. So the normal force in this case would actually be having two different functions. And it would work if the car is going at the right speed, even if the track is frictionless. What about the force causing Neptune to orbit around the Sun? Well, that would be the force of gravity between Sun and Neptune. How about the centripetal force on this ball? That's going to be the tension in the string. Or in the case of this roller coaster train, how about at the top of the loop? Well, in this case, there would potentially be two agents. There would be gravity, and there would be normal force. Now, let's take a look at an example. Let's calculate the tension in a string holding a swinging water bucket in a horizontal circle, and we'll pretend that it's a perfectly horizontal circle. So, we say the water moves to the side so that it doesn't fall out, and the radius of the circle is 1.5 meters. And if we're assuming that maybe this is spinning on a table so that it stays horizontal, if the period of the motion is 2 seconds, calculate the necessary tension in the string. So in that case, we have a mass of 1 kilogram, a radius of 1.5 meters for the motion, and a period of 2 seconds for the motion. Well, the only thing providing a centripetal force here would be the tension. Well, the value of the centripetal force is mv squared over r, but they don't give us v. But here we realize, oh, well, a is not only v squared over r, but it's also 4 pi squared r over t squared, because after all, v is 2 pi r over t. So plugging that in for v, we get 4 pi squared r squared over t squared, all over r. And we cancel a factor of r. And again, I recommend memorizing that a sub c equals 4 pi squared r over t squared is another formula for centripetal acceleration. So in any case, we plug in our givens, and we get a tension force of 14.8 newtons in this case. And again, yeah, I highly recommend memorizing these other formulas for A, not just A equals V squared over R, because it'll allow you to solve a lot of problems much more quickly, and you'll be a lot more likely to know how to solve the problem. What about vertical circular motion? Here, we often speak of things like critical velocity. And in other words, the velocity at the bottom of the loop where the object would just barely maintain a circular path once it reaches the top of the loop. So this will occur when the normal force is just equal to 0. But we're going to examine some situations where the normal force or the tension force is not 0. So let's look at these situations with vertical circles. Let's say you have a swinging water bucket in a vertical circle, and you don't want the water to fall out of the circle. Well, if you don't want the water to fall out of the circle, keep in mind that the water is going to naturally accelerate downward due to the acceleration of gravity. But as long as the net force acting on the water is greater than the force of gravity, that means that the whole thing is going to accelerate faster, more quickly than it would accelerate due to gravity, meaning that there will not be a separation between the bucket and the water. In other words, as long as there is tension in the string, the water will be fine. So let's look at some problems with this. Consider first a situation where a rider is in a car. And think about, okay, what would a rider in a car feel? What force does a rider in a car feel? A rider always feels the normal force. You feel the normal force. You don't feel gravity, because technically gravity is not a real force, though don't tell most physics teachers that, because we do like to include it in our free body diagrams so that we can solve problems with free body diagrams. But you can't feel gravity. You feel the normal force. What does a scale measure? A scale doesn't measure your weight. Your scale measures the normal force that it's applying, which, if you're not accelerating, is your weight. But it's something to keep in mind. You feel the normal force. So let's take a look at the situation at the top. So you have a water bucket swung in a vertical circle. So let's say that you have some tension in the string when the bucket is at the top. Well, what's the net force? The net force is equal to the tension plus the weight, though you don't feel the weight. The water doesn't feel its own weight. The water does feel the result of the tension, or which acts as the normal force from the bucket. But in any case, the net force is the sum of these two forces, the weight plus the tension. That's why I drew my blue arrow here longer. I added the lengths of the weight arrow plus the tension arrow to give the net force arrow. And then that net force is mv squared over r. Well, here's the thing. If that's the net force, then apparently at the top of the loop, tension plus weight equals mv squared over r. So if you want to solve for the tension, you say, okay, therefore, subtract weight from both sides, tension equals mv squared over r minus weight. And then I plug in my mg for my weight, and I factor out an m because I like things to be clean mathematically, and realize, aha, the tension at the top is equal to the mass times the actual centripetal acceleration minus a g. So therefore, the water feels a force equal to its weight times centripetal acceleration minus a g. Or you could say that it feels an acceleration. Like, accelerations are kind of things that you feel. You don't really feel the acceleration due to gravity, but you feel acceleration caused by other things. The acceleration that it would feel would be the centripetal acceleration minus a g, if you divide both sides by mass. Similarly, at the bottom, well, look, notice that the length of my blue arrow has to be the same because we're talking about uniform circular motion. So the magnitude of the net force is always the same. It's always toward the center of the circle. But at the bottom of the loop, that direction has got to be up. But weight always acts downward. So the only way that the net force can be up is if there's a lot of tension at the bottom of the loop. In other words, more than enough to not only cancel the weight, but also to provide a net force up with the same magnitude, mv squared over r, as occurred before. So now, well, here's the thing. How do we figure out the tension? In circular motion, it is always wise to call the center of the circle the positive direction. Well, when you're at the bottom of a loop, the center of the circle is up. When you're at the bottom of the hill, the center of the circle is up. When you're at the top of the hill, the center of the circle is down. So since we're going to call at the bottom of the loop, we're calling the center of the circle up. While the center of the circle is up, we're calling the positive direction up. So we say, okay, tension minus weight is equal to mv squared over r. And remember, the net force is always mv squared over r directed toward the center of the circle, which is up in this case. So that's a positive mv squared over r, just like it was positive at the top of the loop when we called down positive. So we say tension up minus weight, since it's down, equals mv squared over r. So to solve for that tension, we add the weight to both sides, and the tension equals m times v squared over r plus g, or the mass times the centripetal acceleration plus g. So that's the force that something at the bottom of the loop would feel. Or you could say that the acceleration, so-called g forces, if we use units of g's, would simply be equal to the centripetal acceleration plus g. So if they're asking for accelerations felt, you just think, okay, what's the tension or the normal force or whatever it is, and divide by m. So the acceleration you feel at the bottom is the centripetal force plus your weight. Centripetal, and so therefore the acceleration you feel is the centripetal acceleration plus g. And the acceleration you feel at the top of the loop is the centripetal force, or sorry, the centripetal, the force you feel at the top of the loop is equal to the centripetal force minus your weight. That's the result that we got in the last free body diagram. And if you want to divide both sides by m, you'll get the acceleration that's felt at the top of the loop. So, consider an example. So in this problem, this is a four-part problem referring to this situation. Part A is asking, what is the centripetal acceleration exerted on the rider by the track at, and really just what's the rider's centripetal acceleration is probably a better way of phrasing it, if the rider is traveling 20 meters per second at the top. And then part B is how many G's are felt by the rider at the top. And then part C is if the rider was to feel the same number of G's at the bottom of the loop, what would the radius of curvature of the track need to be at the bottom of the loop? And then finally, part D, if the rider's mass is 70 kilograms, what is the centripetal force on the rider? Okay, so for part A, what's the centripetal acceleration on the rider at the top of the loop? So we write our givens. We have our V, we have our R. So the equation for centripetal acceleration is A equals V squared over R. So we plug in our givens and get an acceleration of 80 meters per square second. And then part B, find the acceleration felt and then convert that to G's. Remember, the acceleration you feel at the top of the loop is the centripetal acceleration minus a G. So we get 70.2 meters per square second, and then doing a unit conversion, we get 7.16 G's. That's enough to knock the rider out. Now, part C, what must the radius of curvature be at the bottom of the loop if the rider is to experience the same number of G's? And remember, the diagram showed that at the bottom of the loop, the rider is going 30 meters per second. So the acceleration felt is 7.16 G's, but the equation for the acceleration felt at the bottom of the loop is centripetal acceleration plus g. The idea is that we're going to find the centripetal acceleration and solve that for r, because we're already given v. Because we know that a equals v squared over r, we're going to find the centripetal acceleration, plug in v, and get the value of r. So there's the actual centripetal acceleration at the bottom of the loop. So just if what you feel is equal to a sub c plus g, then apparently a sub c is equal to what you feel minus g. So the real centripetal acceleration is 6.16 G's, the true acceleration. Converting that to meters per square second, we get 60.4 of those. But A is v squared over r, and v is 30 meters per second. So if A is v squared over r, that means r equals v squared over A. So we plug in our numbers, and we get that the radius of curvature at the bottom of the loop must therefore be 14.9 meters. And then what about the force acting on the rider? Well, you would just take the mass of the rider and multiply by the centripetal acceleration. Now, what about more difficult problems? So, for example, more stuff regarding vertical circles and roads and stuff like that. How about calculate the necessary coefficient of static friction between tires and a horizontal, that is, unbanked curve, such that a car would be able to travel at 26 meters per second around that curve with a radius of curvature of 100 meters, exactly 100 meters, well, to 3 sig figs, without slipping. So in that case, we note from our free body diagram, first, that since the car is apparently not accelerating off of the road or into the ground, the net force in what we're going to call the y direction, the vertical direction, is 0. So we'll call up positive. So normal force up minus weight down is 0. Therefore, the normal force is equal to the weight of the car. Yay! So we got the expression for normal force. What about in the horizontal direction? In circular motion, I generally recommend to call either the direction of the acceleration or the direction of sliding, if it's at an angle, the x direction. So in this case, it's just toward the center of the circle. So the net force is equal to, in the x direction, is equal to mass times centripetal acceleration, because after all, it's accelerating toward the center of the circle, which we're calling the x direction in this problem. But what force is that? Well, that's the friction force. There's only one force in the horizontal direction. It's labeled, it's friction force. So the friction force apparently is equal to mass times acceleration. But the acceleration is v squared over r, and friction force is coefficient of friction times the normal force. And we're trying to solve for the normal force in this problem. So we have givens of 26 meters per second for the velocity and a radius of curvature of 100 meters. Now, from the fact that the friction force, which was mu times the normal force, was equal to mv squared over r, we said, okay, well, the normal force was what we got by considering the y direction. The normal force was the weight, mg. So we plugged that in for normal force, and the masses cancel. They better cancel because I didn't tell you what the mass was. And we're trying to get an actual value for these parameters. So the velocity was given, the radius was given, so we plug in our numbers, and we get a coefficient of static friction of 0.69 after we plug in for v, and plug in for r, and plug in for g. Okay. Yay, so we got that. That's about 60 miles per hour, by the way. So that would be fine on dry pavement, but on wet pavement, the car would slip. So you should slow down when driving into curves, especially if it's wet or otherwise slippery, like especially with ice when you have a small coefficient of friction. How about calculate the necessary minimum speed that I would have to apply when spinning a water bucket in a vertical circle without it spilling if the distance between my hand and the water is 1.2 meters, and the hand is relatively motionless, so we just have the radius of the circle being 1.2 meters. So what's the minimum speed that I must spin this in order to not have the water coming out? Well, that's going to be the point where, just like in the case of our vertical circular motion problem from before, referring back to this free body diagram for at the top of a loop, well, here the other downward force in addition to the weight of the bucket is caused by the tension in the string. We're going to look at the limiting case where this tension approaches 0. And in that case, the net force, mv squared over r, will approach the weight. So we're going to end up with an mg equals mv squared over r, because mg will be our net force in this limit as the tension goes to 0, where I'm just barely able to get this thing going in a complete circle. So we have the tension plus weight equals mv squared over r, and taking the limit as tension approaches 0. So Therefore, we just have mg equals mv squared over r. And the mass of the bucket, again, doesn't matter, nor does the mass of the water, because the masses cancel. So we want the minimum speed. So therefore, that minimum speed squared is equal to rg, because we multiply both sides by r. Now taking the square root of both sides and plugging in our numbers. The idea is that the true speed needs to be greater than this minimum speed. So r is 1.2 meters. Plugging in for g as well, we get that the minimum speed is 3.43 meters per second. If I go faster than this, then everything's fine. The water will stay in the bucket. But if I spin it slower than that, that water is going to fall out of the bucket. What about a car at the top or bottom of a hill? It's similar to the bucket of water problem, but there are some differences. In the bucket of water problem, the tension force is always directed toward the center of the circle, because the tension is what's mainly causing the circular motion. But in the case of, and of course that tension is going to change depending whether you're at the top of the loop or the bottom of the loop. But the point is, at the top of the loop, the tension will be directed down, whereas at the bottom of the loop, the tension will be directed up. Whereas the net force is always directed toward the center of the circle, and tension is helping to provide that net force. But in the case of a car on a rolling road, the normal force on the car is always perpendicular to the road. So if it's at the top of a hill or at the bottom of a hill, that normal force is always going to be up. Now, if it's in the middle of the hill, like going down or up, then that normal force is going to be at an angle and things get complicated. But still, that normal force is going to be in varying amounts. At the top of the hill, the normal force needs to be larger than the force of gravity in order for the net force, sorry, that's at the bottom of the hill. At the top of the hill, the net force needs to be down because the hill is curved downward at the top of the hill. So the net force needs to be down, so the normal force would be less than the force of gravity, so the net force will be down. At the bottom of the hill, the net force is up because the curvature is up, and therefore the normal force must be larger than gravity in order to cause that net force to be up. Because, after all, gravity is always acting down. You can't change that. But that leads to something different. In this case, if the car is moving too fast at the top of the hill, the normal force could be 0, and the tires will leave the road. That's our limiting condition in this case. It's just that in the case of the water in the bucket problem, we needed to spin the bucket fast enough so that the tension wouldn't become 0. Here, we need to drive the car slowly enough so that the normal force is always positive. So here's how that works. Again, at the top of the curve, the normal force is still up. It's just not as big as gravity. So in this case, the net force ends up being down. At the bottom of the curve, we need the net force to be up because the center of the circle is up, whereas at the top of the hill, the center of the circle is down. At the bottom of the hill, the center of the circle is up. So gravity is still the same as before, but now the normal force has to be bigger. Well, let's calculate this. Let's see how it goes. Calculate the normal force on a 1,650 kilogram car's tires at the bottom, part A, and the top, part B, of a hill, if the radius of curvature of the road in the vertical direction in both locations is 45 meters, and the car is going 45 miles per hour, which translates to 20.1 meters per second. Well, for part A, we're looking at the bottom of the hill, so in that case, the net force is up, which means that in order for that to happen, the normal force needs to be bigger than the force of gravity, so that for one, it cancels out gravity, and two, there's some extra to provide an upward net force. So we have our givens, the mass of the car, the radius of curvature, and the speed of the car. Net force is mass times acceleration, and since we're given v, we're going to plug in v squared over r for our centripetal acceleration. But since the center of the circle is up, that means we're going to call up the positive direction, because that's the direction of the net force. So therefore, n minus w is equal to positive mv squared over r. So therefore, the normal force at the bottom of the hill is equal to mv squared over r plus w. Very similar to before when we already did this with just vertical loops. And now we'll plug in an mg for our weight, factor out an m, same equation as before, and we plug in our numbers. And upon doing that, we get that the normal force at the bottom of the hill is about 31,000 newtons. So that's about twice the actual weight of the car. What does that mean? It means that if you're at the very bottom of a hill and it's arcing up, since you have more normal force, you can actually stop more quickly. So that's kind of a good thing. What about at the top of the hill? In this case, the normal force is smaller than the weight, and since the net force is down, because that's the direction of the center of the radius of curvature for the circle that we would fit there, we're going to call down positive. So therefore, starting off with Newton's second law and plugging in v squared over r for a, we say that since down's positive, we have weight minus normal force equals mv squared over r. So since that's the case, solving for normal force, we're going to add n to both sides. So it goes to the right side, cancels on the left, and then subtract mv squared over r from both sides. So we're left with n equals w minus mv squared over r, where w is mg. So we plug that in, factor out an m. So this is a somewhat different equation than we had before with the vertical circular motion and tension and stuff like that, where it was v squared over r minus g. Now it's g minus v squared over r, because in this case the direction of the normal force is still up, but the direction of our positive direction is now down. Plugging in our numbers, we get that the normal force in this case is only 1,360 newtons. Remember, at the bottom of the hill, the normal force was like 31,000 newtons. Now it's only about 8% of the car's weight. Very little normal force means very little friction force if you apply the brakes at the top of the hill like this. That's why when you are cresting hills in your car, you should be going more slowly than normal, because if somebody suddenly comes onto the road, then you're going to have your stopping distance is much greater. It's as if you're driving on ice. So that's something to keep in mind. If you're going slowly enough, then it won't be as if you're driving on ice. In the next video, we will take a look at ratio problems and this idea of applying proportional reasoning to solve physics problems. It's a very important video. I hope to see you then, because it incorporates what is an important real-life skill. So hope you all enjoy, and I'll see you next time.